Welcome to exercise number 15 of my series Introduction to Physics. Today we are going to talk about electric fields, and in particular we will focus on point charges. The question is, at a distance of 1 meter there are 2 point charges. Q1 equals 5 nanocoulomb and Q2 equals minus 3 nanocoulomb. Q1 is on the left of Q2. On the connecting line between the two charges there is a point A to the right of Q1 at a distance of 25 centimeters and a point B 25 centimeters to the left of Q2. A, which point, A or B, is on a higher potential, and B, what work has to be done to move a test point charge of Q equals minus 50 microcoulomb from A to B. So what is given? We know that the distance is L equals 1 meter and these individual points are each 25 centimeters, so 0.25 meters to the right, respectively to the left of Q1 and Q2. Then we have given the point charges themselves as 5 nanocoulomb and as minus 3 nanocoulomb. And nanocoulomb implies that it's, in case of Q1, 5 times 10 to the power of minus 9 coulomb. And Q2 is minus 3 times 10 to the power of minus 9 coulomb. In addition, we have the test point charge of minus 50 microcoulomb. And 1 microcoulomb is 10 to the power of minus 6 coulomb. So here it's minus 50 times 10 to the power of minus 6 coulomb. And we are searching for the electric potential and the work that has to be done. So let's make a little sketch first. Well, it's just, the geometry of our charges. So how can we solve this problem? The potential of any point charge, phi, is a function of the distance r from the point charge. And it's equal to minus the integral from infinity to r over e dr. And yes, we can substitute the electric field E as F, the force, divided by Q. But, well, Q, we know it's not a function of the distance. What about F? How can we write down F as a function of r? And the answer is really simple, because we can take F from simply Coulomb's law. And this states that F as a function of r equals to 1 over 4 pi epsilon 0 epsilon r multiplied with Q1, Q2 and divided by r squared. So F is inversely proportional to r squared. So the larger the distance, the smaller the force, which I suppose makes sense. Okay, if we have this, we can put it into our integral. And we see that most of the variables on the right-hand side do not depend on r. So we can put them in front of the integral and solve the integral. So it's basically just the integral over 1 over r squared dr from infinity to point r, or to the distance r to be more precise. And the result is that phi as a function of r equals 1 over 4 pi epsilon 0 epsilon r multiplied with q over r. Now the question may arise, what are epsilon 0 and epsilon r? Well, epsilon 0 is very nice because it's the electric constant. And yes, it's simply a constant. It's equal to 8.854 multiplied with 10 to the power of minus 12 farad per meter. On the other hand, epsilon r is the so-called relative permittivity, which means that no, it's not a general constant for, everything. It actually depends on the material. Now it's very simple if we assume that our charges are in vacuum, because in vacuum epsilon r equals 1. So this is very nice because it simplifies our equation. But does it already help us? We were looking for a system of point charges. To be more precise, we had 2 point charges. Well, in general, for every system of point charges, phi changes slightly. In this case, phi equals 1 over 4 pi epsilon 0, and yes, in general, epsilon r, multiplied with the sum over qi divided by ri. So we basically just sum up over these relations between q and r. And yes, of course, this allows us to solve our problem right away, because in this case it means that phi in point A equals 1 over 4 pi epsilon 0 multiplied with the sum over q1 divided by L1, because our point A is at a distance of L1 from q1, and the second term is q2 divided by L minus L1, because point A is precisely L minus L1, this distance away from q2. And we've given all these variables in the basic units, so we can calculate phi right away, and we get that phi in point A is 143.8 volt. Wait, what about this unit volt? Where does it come from? Because phi, if we have a closer look, we see that epsilon 0 was farad per meter, Q is in coulomb, and the length again in meter. This doesn't look like volt, does it? Well, actually it does, because farad per meter is nothing else than ampere second per voltmeter. And on the other hand, we can actually write this in a slightly different way and then also substitute coulomb. And yes, all that's left over is actually volt. So this is very nice. What about the second point? We were supposed to compare phi in point A with phi in point B. But this is really easy because we already saw above here that everything is given. We just have to take, the right Q's and the right L's. So phi B equals 1 over 4 pi epsilon 0 multiplied with Q1 divided by L minus L2 plus Q2 divided by L2. And what we get is that phi B is actually equal to minus 47.9 volt. And yes, this answers our question in an absolutely simple way. Phi A, the potential in point A, is larger than the potential phi B in point B. Yes, this was the first part. The second question was, what about the work to move a test point charge? And in general, the work to move something like this would be minus the integral over f dr, and we have to integrate from point, say, P1 to point P2. And yes, we can substitute the force again as Q multiplied with E, and since Q is, in our case, this test point charge, and yes, it does not depend on R, we can put it in front of the integral. The question is, can we solve it? And the answer is, well, yes, if we go at it with, some feeling, because we have to integrate from P1 to P2 over EdR. And we just saw that, phi is actually minus the integral from infinity to a certain distance r over EdR. Can we use this? Yes, of course, with, a tiny trick. Let's simply split up the work. So you can see here again the equation for the work, and we can split it up. It's exactly the same if we write down the work W equals minus Q multiplied with the integral from point P1 to infinity over EdR, and then plus the integral from infinity to point 2 over EdR. So we basically do not go from point P1 to point P2. we move from P1 to infinity and then back from infinity to point P2. And this is really nice because we can slightly rewrite it. You can see here that if we change, the borders, the limits of our integral, we change the sign in front of it. And this actually allows us to use the definition of phi, because it simply means that the work W equals minus Q times phi in point P2 minus phi in point P1. And yes, in our case here it means that W equals minus Q multiplied with phi B minus phi A. Perfect, because we have given or already calculated these values. So we can just put them into the equation, and what we get is that the work equals 0.0096 joule. So it's actually very small, it's just 9.6 millijoule. And yes, this answers our question. And this is it for today. I hope it helps you when you're especially starting with this topic to understand it a bit better. If it did, consider subscribing, give me a thumbs up and leave a comment below. And I hope to see you soon for another video, and until then, stay healthy, especially in times like these. And I really hope to see you soon. Bye!